We are now in 3.5, which is polynomial and rational functions and their graph. So remember, rational is with the fraction, and so we are going to look at their graphs. So part one is going to be find the domain of rational functions, use arrow notation, identify vertical and horizontal asymptotes. So let's go ahead and get started. So rational function is whenever you have a polynomial on top, polynomial on bottom, they're being divided. You do have to remember that q of x cannot equal 0, because when that happens, that causes an undefined area or point. So that is what we have to make sure it cannot be 0. So what that's going to do is that's going to make it where we can do our domain restrictions. Okay. Anything that makes this denominator equal to 0 is going to be things that x cannot be. Okay. So if we're just looking at the domain of this function, we do know that this cannot equal 0. So what we'll do is we will set it equal to 0 to find out what x cannot be. So that tells me x cannot be 5. So that's how we can restrict our domain. One way of writing our domain would be to say x such that x does not equal 5. Another way to write this would be we're going to go negative infinity to 5, not include 5, so we have to use that parentheses, union that with 5 to infinity. So what this does is it's everything except for 5. So that's one way of writing that. Something that you will see that we're going to do on f of x is simplifying it. This x squared minus 25, that's a perfect square. So we're going to have to factor that perfect square. So this is just a kind of a preview as to what we'll see. You take the square root of this, you take the square root of that, and you write it as the difference of squares. Because this is a perfect square, so this is actually difference of squares. So that would be x plus 5, x minus 5, and then you have the x minus 5. And then they end up simplifying out. But you still have to do your domain restrictions even if you can simplify it out. Because if x is 5, we still get a 0 on the denominator. So let's look at the next page. On the domain of this. So again, we want to, this was a mistake. It should have said 25. So fix that. That was a mistake that I forgot to fix. So what we have to look at is x squared minus 25. It cannot equal 0. So we're going to solve it out. So this again is that difference of squares. X minus 5 or x plus 5, x minus 5. So whenever you have that, you would set both equal to 0. So remember, this cannot equal 0. So subtract 5. So x cannot equal negative 5, and then add 5. X cannot equal positive 5. So it's everything except for negative 5 and positive 5. So two different ways of writing this would be domain x such that x does not equal plus minus 5. You could use that notation. And then the other way would be we're going to go negative infinity up to, we're going to do negative 5 first because that's what we'll hit first as far as the x value if we're going forward. Union that with, we want negative 5 to 5. Union that with 5 to infinity. So what this tells us is everything except for negative 5 and positive 5. If you have, this is just an extra example, 1c, let's say it's 1c. Let's say we have h of x equals x plus 5 over x squared plus 25. So if we look at that, we would say x, sorry, I'm going to kind of do like this. X squared plus 25 cannot equal 0. So if we were to solve this out, these are both perfect squares, but it's not difference of squares, it's sum of squares. So you can't really do that. So we'll have to solve it this way. X squared cannot equal negative 25. Well, think about it. If I square something, I will always get positive values. So if I take the square root of that, that's going to be imaginary. So this has no restrictions at all on the domain, because that is going to be x squared. Well, x cannot equal, you do the imaginary plus minus 5i, which is imaginary, so that doesn't have any restrictions at all. So your domain on the h of x is no restrictions, negative infinity, positive infinity. So it's finishing that problem out. Okay, arrow notation. Use arrow notation to describe the behavior of the function. So x going to a positive. X approaches a from the right. Okay, so that's positive going from the right. From the right. X approaches a from the left. X approaching infinity as x increases without bounds. X approaches negative infinity as x decreases without bounds. So that's the arrow notation. So we'll look at our vertical asymptote. Okay, so let's look at this. It says the line x equals a is a vertical asymptote of the graph of a function f if f of x increases without bound as x approaches a. So we are approaching from the right. So think about left and right. As we approach from the right, it is going up to infinity. This is a, right? This is the horizontal line, x equals a. So as you approach x equals a, it's going to positive infinity. If it went down like that, then we'd say it's approaching negative infinity. So it says as x approaches a from the right side, so see how that says plus from the right, x is going to go to f of x, which f of x is the same thing as y is going to infinity. So then let's look at this one. It says as x approaches a, so remember this is our line, our asymptote, x equals a. As it approaches it from the left, so this is left and right, as we are approaching from the left, it's also going to infinity. Y is going up to infinity. Okay, let's look at whenever we're approaching x again. X equals a is our line. As we're approaching from the right, that's what that a plus means. That means from the right. Instead of it going up like this one, it's going down. So it's going to negative infinity. It's going down, 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 down to infinity, negative infinity. This one says as x approaches a from the left side. So this is my left side. This is right. From the left, it's approaching x equals a, but it's going to negative infinity. So you've got to know which way it's going, so that way you can graph it. So let's look at the next page. So locating our vertical asymptotes, we are going to look at our rational function, look at p of x and q of x. This is our numerator, this is our denominator. If they have no common factors, a is a 0 of q of x, the denominator. Then x equals a is our vertical asymptote of the graph of x. So you've got to look at q of x. You've got to look for zeros. So here's our first example. So we have x over x squared minus 1. So we want to factor this. These are difference of squares. This is x plus 1, x minus 1. We're able to factor it. And then we look for our zeros. So this is, remember how we did our domain restrictions, where it can equal 0 on the denominator. So we're going to do that same thing. And this is where we're locating our vertical asymptotes. So x cannot equal -1, and x cannot equal +1. So if we look at where x, remember this is our x-axis, at -1 and x at +1, these are going to be our vertical asymptotes. X equals -1 and x equals +1. So you would put a point there, draw dotted lines or dashed lines to identify where x cannot be. So that makes a vertical asymptote. Okay. So then finding vertical asymptotes of a rational function. Here's another one. This says, it gives us an example. So look at x squared plus 1. I can't factor that, but I can set it equal to 0, see if we have any restrictions on our domain. That's 1, that's 1. X squared cannot equal -1. If you take the square root, you get x cannot equal, this is imaginary, so it'd be plus and minus I. We couldn't factor that. That's why we didn't factor it. So it becomes plus minus I. So there's not any. We cannot factor the denominator of h of x over real numbers. The denominator has no real zeros because these are imaginary. Thus, the graph has no vertical asymptotes. So we can't make any vertical asymptotes here. Okay, now let's look at horizontal asymptotes. Horizontal means it's a horizontal line. Horizontal lines are written as y equals some number. And if you think back to slope dude, a zero slope, it's like y equals 0x plus some number, b. That's a zero slope. Slope dude, 0 fun, m equals 0. So this is a horizontal line anytime you have y equals a number. So that's how you'll write your horizontal asymptote. So you're going to do how it approaches it. So as x approaches infinity, so think of x here. As x approaches infinity, x goes to the right, from left to right. Not from right to right, from left. I guess I could put it from left. As it approaches, x is going to go to infinity. And then f of x is going to approach b. So as x approaches infinity, the y is only going to be here. It's not going to go above it. As x approaches infinity, so as you're going from the left to the right, our y value is going to approach b. So see how it skates along that value, that line, that horizontal line? Okay, this next one, as x approaches infinity, so even though it crosses it, now it's going to skate along it. F of x is going to approach b. So let's look at our horizontal asymptotes, how to find them. Here are the instructions. So it says, here's our function. We have two polynomials where an is not 0 and bm, so our leading coefficients are not 0. They have the same, or they both have x to an n, and this one has x to the m. So it says the degree of the numerator n, the degree of the denominator m. So you're looking at these two, and these are our leading coefficients. So a reminder would be look at the exponents of your leading coefficients. So these are my leading coefficients. They're going to have the highest exponents, and you're looking at those two. So it says if n is less than m, the x-axis, or y equals 0, is our horizontal asymptote. X-axis is our horizontal. If they're equal, then you're going to divide your leading coefficients, and that's going to be your horizontal asymptote. Now, if n is greater than m, then it's going to have no horizontal asymptotes. So you have three options. You have the x-axis is your asymptote, you divide them and get your horizontal asymptote, or there's no horizontal asymptote. So it says we need to look at our exponents. So look at these. So this is my n equals 2. M is my leading coefficient of my denominator, that is also 2. So that tells us n equals m. So that means it's number 2 from our last slide. So that means I'm going to do y equals a n, sub n, and b sub m. So if we look, that would be 9 is our leading coefficient, and 3 is our leading coefficient, which gives us 3. So y equals 3 is my horizontal asymptote. So remember, it's a horizontal line where y is 3. So you put a point there, draw a dotted line. That's y equals 3. Okay, let's look at the next one. N is my top, so that would be 1. M is my bottom, which is 2. So now it says N, which is 1 compared to 2m. So n is less than m. So n being less than m is going to be number 1. So our horizontal line, or asymptote, is at the x-axis, or y equals 0. So see how y equals 0? It's a dotted line on the x-axis. Okay, I forgot to change this. This should be 3, because we need another example. That's the same as the first one. We want to change it up. So that should have been 3. So go ahead and change that. So let's look at n equals 3 and m equals 2. So n compared to m, so 3 compared to 2. 3 is greater than 2. So that would be number 3. So this is no horizontal asymptote, none. Okay, let's go to the next page. Part 2. Part 2 starts with graphing. So let's just look at the basic reciprocal function. So this is like your parent function, y over x is going to go like this. You're going to have your vertical asymptote is x equals 0. And your horizontal asymptote is going to be at y equals 0. And they're going to go in opposite directions. This one, and that would be because my exponent here is greater than this exponent. So that's why we get that for our horizontal. And x cannot equal 0 is our vertical. Then we have this one. So you're going to have the same thing. Vertical asymptote is x equals 0, and our horizontal asymptote is y equals 0. But they are both going to go in opposing directions there. Okay, so that's the end of part 1.